Hey everyone, so let's now talk about how to create curves with vectors. We start again with a point wrangler that we set to detail so that we can create stuff from scratch. And the first thing we have to learn is, since curves or edges are made of points, we always have to start with points. So let's create 2 points here, and we already saved them in a variable. And we do this, of course, with add point. And then in the current geometry, I want to create a point with a position 0, 0, 0. And there it is. This has worked. I'm not sure why I see this kind of visualization. And there is the point. There you go. And now let's create another one. I just copy the whole thing and call this new point 2 and move this in x by 2 meters, let's say. There you go. And there we have a second one. So this worked. 2 points. Perfect. Now, as you might have seen in other contexts, curves in Houdini are primitives. So the command, when we know for points is add point, the command for add primitives is actually add prim. And then it has multiple inputs. A geo handle, okay, which is 0 probably, and then a string type. And this is where we have to look into the help what this means, because it's a string. So it defines what kind of primitive we want to create. So here's the help. And we're talking about this here type. And here we have poly, polyline, tet, sphere, circle, tube, metaball, and so on. So what we want to concentrate on is polyline. So poly, we will talk about in another video. This is, of course, to create polygons, so faces. And then, interestingly enough, there are tetrahedrons we can create, like in vellum, and also spheres and metaballs and all kinds of other stuff. So we will concentrate here on polyline, because this means basically a curve. And as we've seen, the inputs here are, well, multiple options. We have just the handle and then the name of the type, which is polyline. But there are also more options, and that is that you can add the points right after that. And this is actually something we want to talk about. The quickest way of creating a line is just to use an add prim and then add the 2 points you want to add as a minimum right away. But before we do this, let's actually do it this way, just a polyline, and we do not add anything to it. And then of course we finish with a semicolon. And just for you to understand, we now actually created a primitive. It's just that we don't see it, because this absurdly is basically a line consisting of nothing. So those 2 points that we created are not automatically part of the curve that doesn't exist yet. So be careful, you can actually create primitives that are not, filled with anything or not connected to anything, even though that might seem a bit weird. Now, again, the first way of doing this is simply to use the point number, not the position, but the point number. And this is saved in NP for our 2 points. So NP and NP2, we can just add this at the end, and now we get a line between the two. So this is easy to understand. We could even create one in the middle of it. Let's call this NP1, for example, to not be being too confusing. And now what we could do, and be careful, it looks like this point here is part of the curve, but if we select it and move it, we haven't added it yet. So if I move it away, it doesn't move, the curve doesn't move with it. So be very careful what you're doing and don't assume anything. Currently, we created 3 points and we only used 2 of them, and the third one is still just a point. Now, how can we add this point to our setup? Maybe quickly, let's turn the background black because it's really hard to see everything. There's the point we're talking about. We can actually just add it at the end, NP1. But be careful now, this is not connected in the middle of it, but it's actually the next point after NP2, and then the connection goes there. So what you can do, though, is you can change the order, but that's my point here. The order is important. If you do it this way, then you can see, and this is actually visible in the numbering, we added the first point, NP, which becomes the point 0. The second one, NP1, becomes 1, and NP2 becomes 2. So the order matters, and let's change this again while we see the point number. There we go. What might be a bit weird, though, is that the numbering hasn't changed, and that's because the numbering actually comes from the add point up here. It's then just added differently. So this curve is actually made of 0, 2, and 1, not 0, 1, and 2. I think you get the idea. Now, as an alternative to this, you cannot just add all the points at the end. You can just leave it out like that and just create an empty primitive, so to say. Let's do this. And then, of course, I don't see any primitive because it's not consisting of anything. But I can also now use the return of this command or this function to attack this empty primitive. And I call this nprim, for example. So if we look at the help again, you can see just like with the add point before, it has an integer in front, which means this function gives back an integer. And somewhere here it's actually explained what this integer is, just like with the add point. It's the primitive number. Why is this important? Because when I create a primitive that is empty, I can still add points to that primitive. And that you can do with the add vertex. And we learned about this before, what a vertex actually is. A vertex is a part of a primitive. So the points that are part of a curve are also called vertices. So what can we do here? How does add vertex work? Pretty simple, really. It has three inputs. The geo handle, which is 0, of course, so we don't create geometry somewhere else. The primitive number, and this is now the new primitive that we just created, saved in nprim, and then we add the point number to add a point to this primitive. So in this case, it's just nprim, and then we just add one point to this curve, for example, np, which is our first point. Now, of course, that didn't help us much yet. Technically, we now have a point as part of the primitive, and as you can see here, now we have one vertex that is part of one primitive. But of course, to see something, we need a second one, and this is why you just run this command again with a second point, for example, np1, and then you run it again with point 2. I prefer working this way. This is how I usually do it because I think it's easier to understand. You first create the points, then you create an empty primitive, and then you add the points to it. Makes it very easy to work with, and also later on, as we will see, it makes it easy to work with a for loop. Talking about the for loop, let's go back to our example from the last video. Because there we created a sin wave or a sine wave, and I just realized I should have scaled up my vex. I always forget that. And as we remember, what we did here is we ran a for loop for, in this case, 100 times, and let's see where they are there, and then we created points that defined a sine wave. Now, as we've seen before, we can just use an add here with the polygons by group to connect them. So there's a lot of stuff that I will show you that is not absolutely necessary to do with vex. But in this case, what we can do is we can do the same as we did before. We can actually, in the beginning of the whole thing, create a new primitive, an empty one, with nprim equals add prim. And then what kind of primitive? A polyline. And then we just don't add anything. This is now an empty, kind of broken primitive. And after we created now each point, we can just right away after that, and we have to make sure that we know actually the new point number of this point, we just add this as a vertex of our new primitive. So in this current geometry, I add to the nprim primitive, which is our curve, the new point. And here you can see with every loop, the np will be overwritten with the next one, but that's fine. And boop, as you can see now, every single time a point is created, it will also be added to the existing curve. And this is why we have one primitive with 100 vertices. Now, of course, I could add one line for each point, which is a bit more complicated because then you would need to find the second point, which is either the last one or the next one. So you have to do a little bit of shenanigans to figure this out, which one this is. But maybe we could play around and do something stupid like this. We just create a new curve and then just add one new point on top of this at the center or something. So maybe 0, 0, 0. There you go. And then we add this first point to our curve. And then what we get is this, that every point is connected to this point at 0, 0, 0. Or maybe if this is a bit too stupid, maybe do something like this. I don't know. Or maybe 40 in x. Yeah, and then minus 20. And you get something like this. I don't know. Maybe this is some interesting shape you're looking for. So my point here really is that you can play around with how to create those curves. The good thing is, you know, you have complete control about where your points should be created. So this is kind of useless, I understand, but let's look into something we can do with this. One thing you can do with this is we can generate curves on the fly. So for example, if we wanted to cover this sphere here in hair or something, we could scatter on it, and then sure, there are other ways of doing this. We could copy a line to it or whatever. But we can also just do it directly in vex. So we can add a new point, And this new point should be the same position as the current point we're running over. And you can see we're now running actually over points instead of creating them from scratch. And for each point, we add another point with the current position of the point we're running over plus the normal it has. Now, currently this will not work because we don't have a normal. As you can see here, it just created it because it saw it in the code. So let's create a normal on the points of the sphere. And then we have also normals on the points that we scatter. And what we get now is this. We create for each point another point that is moved outwards in the direction of the normal. And we can, of course, multiply that with a distance parameter or something. So something like this. And now what we can do is, of course, we save this in an attribute so we can use the point number later. And then we create a curve for each point with the @prim. And this is a polyline between the new point and which point? Well, the current point. And what's the point number of the current point? Of course, ptnum. So you can use ptnum as part of your curved creation. And then you get this. And now you have created for each point a curve in the direction of the normal, which again, can do this in other ways, but it's kind of handy that you can do this in a single node. What you can also do, for example, is instead of pushing it into the direction of the normal, you can just push it in any direction with a curl noise, for example. And then it's just, random directions, maybe make it a bit smaller and also make it a bit shorter. And then you can get something like this. And now each point, is based on the current position plus a random direction based on a curl noise. Another thing you can do, which I do quite often, is instead of creating curves, into some direction, I actually try to find a position on another object. And we know, of course, for this we have the min-pos, and just create a connection between the two. So for example, I take again, I'm still running over the points that I just scattered, but I'm looking for another position, the close position on the second input with the min-pos. So relative to my current position, I find the closest position on the sphere 2. And then I create a primitive curve. For now, it should be empty, and let's save it somewhere so that I can use it later. And I want to add to this empty curve 2 new points. My current point with ptnum. Okay, I can already do this. This works, no errors. And then I create a new point at the position of the closest point on the sphere. So it's an add point, and the position of the new point is close P. And this one I add as well to my curve, and it lives in NP, of course. Now I get this. It's a bit too many points, but here you can see the idea. The second sphere is now always looking for the closest position and creates a curve there. We will use this actually in another video later on, but in this case I want to use this for something else. And that is, imagine we have something like a plasma globe or something, and I want to connect curves between an inner sphere and an outer glass sphere. So I can move my second sphere back and just make it bigger. And let's actually make sure my first sphere is at the center as well. There you go. And you can see I can now create connections between the two by just looking for the closest point, and then any point will connect to it. And of course, what I can then do, which is possible in Vex, if you want, you can try that. But I think in this case, it's easier to just resample the curve that we get now. So before it was just a curve with 2 points, and we resample it, and then we can just add a noise on top of this. So we take the position and we add to it, and not just positive, but 0 centered. And let's make it a bit less strong and a bit less extreme. And then we can animate this as well. And then it looks like this. Let's make it faster. So like this. Now, okay, we can see that unfortunately it pushes some curves through. So, okay, I didn't expect this. In this case, maybe an attribute noise is less good. So let's quickly fix this with Vex. So we do the same thing. We want to add to the position of each of those points a curl noise, of which we want to be able to control the size and the strength, just like before. And this will not help us much. We get the same problem that some of the points push outwards. But what we can now do is we can use the curve u that we can calculate in the resample we already have, which, as we know, creates an attribute between 0 and 1 between the beginning and the end of each curve. And we can just use this, and let's actually put this into a noise float, because now we can multiply this noise float with a ramp. And the cool thing is the curve u is always between 0 and 1, so we can use it directly as an input. And what this means is we can now create a ramp that says along the curve of each electricity line, how strong should the curl noise be? Something like this. And then we can say on the edges, the first and the beginning and the end, there should be nothing. And of course we have to animate the whole thing. So for example, with an offset vector, something like this. And we can then, I don't know, animate this with $F or something. And then we get this. Let's make it a bit stronger and maybe a bit bigger. And there is something wrong because you can see that all the curves are moving in the same direction. So it seems like the vector is not in all directions. So I'm assuming there's some kind of data conversion problem. So this is a vector. This will be a vector. I think maybe this one is not a vector. Let's try to turn this into a vector. Still doesn't work. Oh, I know. I made the mistake of turning the noise into a float. But this is a curl noise, so it has to be a vector, of course. And now it works. Okay, fair enough. See, it can happen to me as well. And now you can see this is happening. And to make this a bit more interesting, we can make the inner points move. And this is just in the scatter, changing the global seed constantly. Maybe like this. And then you can see, maybe with a fewer points, you can create some kind of electric plasma ball effect by creating those curves directly. And in this case, we then create noise afterwards based on a ramp using curve u. And let's make this quickly look nicer by giving the inner sphere a darker color, merge the whole thing, and give the second sphere a transparent material. So yeah, so this is what you can do by creating your own curves. We will look later on at other examples of working with curves. So I hope this is helpful. Thanks very much and see you later. Cheers.